Hello and welcome to a webinar on microplastic analysis with FTIR spectroscopy. I'm Marten Seeba, an expert for microplastic analysis, among other things, at Bruker Optics. And I'm really glad that so many of you could join today. And for everyone that attends, we also have a list of further resources and reading provided along with the webinar, because we cannot go into detail on every topic. But we'll just scratch the surface in some aspects, and you can read up on this if you like using this material. So without any further ado, let's jump right into the presentation. So what will we talk about today? So first, analytical methods and why and when you should use FTIR. Then there's the experimental setup for sample pre-treatment and filtration, so laboratory equipment, how to minimize contamination, pre-treatment of different samples and their filtration. Then analytical considerations regarding FTIR microscopy and imaging and how to automate the measurement, and also how to automate data evaluation. So the less effort, the better, the higher the throughput in the end. And show you a few examples with hands-on from sea salt, river sediment, and also from milk. So there are many different analytical approaches. One of them, for example, is visual microscopy in combination with Nile red staining. That is an agent that colors all plastic particles but not other particles. But this is not very reliable as you're doing this with the naked eye. So this is very tiring, very time consuming. And you have no polymer identification, so you don't know what kind of polymer you actually found there. A very common and very good technique is pyrolysis, GCMS. Here you get very precise information about the mass distribution of the particles and the identity of the polymers as well, but you get no information about the particles. And this is also a destructive technique where the sample is destroyed during the measurement and you can only have small amounts per run. So you need to prepare your sample quite extensively to have it in a quality that it can actually be measured by GCMS. And then there's vibrational microspectroscopy. This gives you exact information about the particle identity, size, and the numbers. And this is the most important information to assess any biological threat the particles you find might pose. It also gives you a rough mass estimate, but it's really very rough only. And it's a non-destructive technique. So your sample will be alive afterwards and you can measure it again in case you want to have a look at it again. It's also the fastest method available to obtain results and the most cost efficient regarding material needed and also labor time. Okay, so this is why we're talking about FTIR and we want to focus on this today. But to do FTIR spectroscopy, we need FTIR spectrometers. And here we have two analytical instruments, and these spectrometers are on the one hand for macroscopic particles, so the ones that are quite large or too large for a microscope, and this is our Alpha 2. It's a very compact FTIR spectrometer that comes with interchangeable accessories. So this is an ATR accessory which will be used for polymer measurement. It's quite robust and reliable, very little to no maintenance. And the integrated touch panel you see at the back makes it independent from any bigger PC or laptop for its operation. And for microscopic particles, we have the Lumos 2. It's a standalone imaging microscope. That means it doesn't need any base spectrometer, and it's all over compact design. Also enables high light throughput and very little loss. It's fully automated, so there is no user interaction required, for example the ATR crystal or the imaging of the filters. So it's fully automated, everything controlled by the software. And it offers the fastest imaging speed with the focal plane array technique. But a little back to our laboratory equipment. We need for sample preparation basic glassware, beakers, steering rods, maybe a funnel. Basic chemicals for sample treatment like potassium hydroxide, zinc chloride. Petri dishes for filter storage or any other storage option, and very important, we need a particle-free water supply that we're not contaminating our sample. For the filtration, we probably need mesh sieve filters to do a pre-sorting of the large particles from the smaller ones. Anodisk filters for the filtration or the final filtration of the particles that are measured with the microscope. A filter holder, a suction flask, a vacuum pump, which makes the setup look something like this. What can you do to reduce contamination? What equipment is required? First, airborne particles are basically everywhere. So air filtration is very important. Best done, it's in the filtration in the ventilation system. Have some overpressure in your lab, that the filtered air is pressing out the air that is unfiltered and would come from the outside to induce contamination. And for quality control, you can have a particle counter in your lab. But this is all quite complicated and maybe a bit too much. So there is also a laminar flow bench. This is a somewhat more simple setup where you have with the number 1 where air comes in, it's collected at the place of entry. At number 2 goes through a filter that all particles are removed, and then by this pump it's pumped downward to create a constant airflow and overpressure just in this area to protect your sample, also with an outward airflow that stops any air from entering in this chamber. And this already reduces the contamination by a factor of 25. So this is what a setup could look like. This image was taken at Wessling, a contract lab with a lot of expertise in microplastic analysis and also some Bruker equipment. So what to do to reduce contamination? Always use metal or glass equipment where possible. So there is no intake of any kind of plastics from the equipment. PTFE is also a possibility because it's almost never found in any samples and is also so unique that you will be able to identify it. And in measurements with anodisk, you will not see them anyway. Wear proper clothing in the lab. So a lab coat is important, wearing a hairnet, avoid synthetic fibers altogether to not contaminate your sample with microplastic. The use of filtered water, as we have mentioned before. And very important is the measurement of blind samples as reference. So just measure the empty filters to know what is your baseline on particles that you will get, which you have to subtract later, and then filter your lab water without any sample to see how much contamination or how many particles you may add to this to get a baseline. And now we come to sample preparation and how to remove contamination. So for drinking water, beverages, beer, anything like this, you can directly filter it, wash the filter a bit to get rid of the remains of the original liquid, and then let it dry and you can measure it. If you have something like river or seawater sediments, something that is more complex and has a lot of, well, soil in it or sand, you will need to do a density separation to remove all of this and just get the plastic particles. A bit more on this on the next slides. And these may also have a biofilm or other biological contaminants on it, and then you need to do oxidative, alkaline or enzymatic treatment to remove this. If you have food like yogurt, fish, mussels, anything like that, you will also need to do a treatment to remove all the organic parts that contaminate your sample, and then you can do the filtration. Okay, a bit more on density separation. So how do you do this? By submersing your samples in a saturated saline solution, and in this case the plastic swim. sand and other contaminants sink to the bottom. Plastic usually has a density of 1.4 or lower, and this is why you use saturated solutions of zinc chloride, sodium iodide, or potassium formate. And again, you mix your sample, you stir it well, and then in the end the sand will sink to the bottom, the plastics will swim, and you can just pour it off. These salt solutions can be recycled by filtration, so you're not generating a lot of waste by using this method. To remove organic material, there is the possibility to do this with enzymatic digestion. This can be done in multiple steps, or you can do it in a big bulk process, and it can be combined with another treatment method. There is alkaline degradation. So in most cases you're using a potassium hydroxide solution of 10% and heat it up to maybe 60 degrees Celsius. But this may also deteriorate some polymers. And there's oxidative treatment with hydrogen peroxide. This is actually very effective, but it also may deteriorate some polymers and therefore interfere with your results. There are also some less common options, like the acidic breakdown with sulfuric acid and nitric acid, but this is with concentrated solutions, and so this is very dangerous and difficult to handle. And there's also the Fenton reagent, which is quite effective without any side effects, but the handling is also not the easiest. Okay, when our sample is finally prepared, the remaining solution has to be filtered. This is mostly a two-step process. So in the first step, we are filtering off large particles, for example, everything that is above 500 micrometers. And for example, you can use mesh sieve filters in one or multiple steps, depending on the sizes of particles you encounter in your sample. We need to remove large particles because they absorb all the IR light in microscopy. And for this, we're using the alpha 2 spectrometer. And here I want to talk a bit about the principles of FTIR spectroscopy so you understand why we're handling things the way we are. So first, how does infrared light interact with matter? It interacts with molecular vibration. So this is vibrational spectroscopy. And this is a water molecule, oxygen in red and the two hydrogen atoms in white, and they can stretch apart in a symmetrical fashion, which is one band you will find in the FTIR spectrum. They can also do this in an asymmetrical fashion, so this is another vibration we will see in our spectrum, and there are some more, but this is enough as an example. And how do we measure these vibrations? So we have an IR source that emits IR light, and our sample that absorbs some of the light according to the different vibrations it has, and then we collect the transmitted light on a detector. We do this for all the wavelengths simultaneously, and we need to do Fourier transformation with this data to get the final spectrum, which you will see here. This is a polyamide example. Okay, how do we use such a spectrum for identification? An FTIR spectrum is like a chemical fingerprint, so it's unique for every individual compound and for every polymer type. So we can compare it to a reference database, and in this way we can identify them. This is done in routine applications and quality control, for example, of incoming goods, for pharmaceuticals, also for polymers. And when we combine the microscopy with the identification, we can also identify microplastics. And to identify microplastics, we need a good reference database to have all the spectra available in the best quality there is. And for this, we have teamed up with the Kunststoffinstitut Lüdenscheid, a polymer institute based in Germany, and have created a very reliable database with lots of information on different aspects of the particles and where they were manufactured. And they were measured on our spectrometers and re-verified by the Kunststoffinstitut, so the Polymer Institute. And we keep this library always up to date. That means we have an annual update with new materials that you might find that are of high relevance for the polymer industry, but in conclusion also contains all the materials that you will find in products that break down to microplastics. And we have an excellent material coverage with over 1,000 polymer spectra, and we have all the common but also very rare types of polymers like polylactic acid in there. But it's always best to demonstrate this using a live example. So this is again our Alpha 2 compact FTIR spectrometer. This is one of the many exchangeable accessories, in this case a high pressure ATR with a rotatable clamping arm. And this one here is a piece of plastic just about 5 millimeters in size. And I will just place it on the ATR crystal, close the arm, and you will already see a preview spectrum here. So you know it's in good contact, and when you tap the Start Sample Measurement button, it will automatically run the measurement. You will see the progress in this bar, and when the measurement is done, it will automatically check in the KIMW library for the best matching result. And you see in red the measured spectrum, in blue the result, and this is clearly a polyethylene sample, high density, and this way you can identify all your samples that are larger in size or too large for microscopy. The second step of our filtration, so after we have removed all the particles that are too big to be analyzed by the microscope, we filter all the small particle onto an IR transparent filter, because we will not measure them in ATR, but we will shine light through them. We will measure the particles directly on the dried filter, and before you finalize this, the cylinder walls should be rinsed multiple times because the particles tend to stick to them, and also wash the filter thoroughly to remove any contamination or remains from the treatment of the sample. The use of vacuum filtration is advised to speed up the filter process, and you can obtain such a basic filter kit directly from Bruker. So what kind of filter do we recommend? Anodisc is the most used filter material at the moment. This is because you can measure the sample directly on the filter and you do not need to transfer it later and maybe lose some of the particles or contaminate it otherwise. And you have almost no loss in IR transmission above 1250 wave numbers. The spectral range is from 4000 to 1250 wave numbers, so not full IR, but enough to identify all the particles that you may find on your filter. It's suitable for imaging and mapping in transmission. What this is, I will also explain a bit later. And you have a pore size of 0.2 micrometers, so all the particles will be captured. There is no way you're missing anything. The suggested diameters of these filters are 13 or 25 millimeters. The picture you see here is 25 millimeter with a support ring, because these filters are quite brittle and their stability is greatly improved if they are if they have this support ring. So when you put this together, the setup will look something like this. You have your suction flask, the carrier frit where you place the filter on, a cylinder to hold it in place, and also here you fill in your sample, and a clamp to secure everything tightly. And when you now fill in your sample, you apply vacuum here, that the sample is pulled through the filter to speed up the process. But there are also other filters. So there are silicon membranes. These have also a high IR transmission without fringes, a little less than anodisc. We have a full range available of the MIR region, so 4000 to 600 wave numbers. If you're using a focal plane array detector, down to 750. But again, this is more than enough to identify everything you may find. These filters come in different sizes and shapes, and we have pore sizes down to 10 micrometers available. And this is dark field compatible as well. So this is a contrast enhancement technique. If you're looking to manually or automatically find single particles on this, this is a very good option. There are PTFE filters. They can be used in transmission mode as well and have the same spectral range available, but they have their own absorption between 1100 and 1300 wave numbers. But this does not really interfere with the identification, and you have no IR loss above and below this value. So these also very good transmission filters. And there are also gold coated filters. These are only used in reflection mode. There's nothing that limits their MIR range, so the full range is available. You get a good visual contrast, and this is also dark field compatible. These are mainly used if you also want to do Raman analysis on the same filter. Otherwise, reflection mode is only the second choice after transmission, because you get artifacts and also total absorption quite easily with this kind of filters. Then there are cellulose or glass fiber filters. They can only be used with ATR. And ATR mode can be quite time consuming because you have to constantly clean your crystal, because it can cause cross-contamination if one particle sticks to the crystal and you're moving it to the next one. But these filters are cheap and easy to handle, and if you want to do this, really depends on the number of particles you expect on your sample. If it's just a few, this is a good option. But otherwise, we would really recommend to stick to anodisc. Okay, now we have prepared our lab with the right equipment. We have treated the sample, filtered off all the large particles, and have our microplastics on an appropriate filter for microscopic FTIR analysis. Now we have to decide what kind of analysis we want to do, mapping or imaging. And to explain the difference, imaging is a method for spatially resolving the chemical properties of a sample. So in the end, you know what kind of chemical is at what position, and in our case, what kind of particle is at what position. And we create pixels, and each of this pixel contains a whole FTIR spectrum. So if you have a single element detector, you're doing every pixel consecutively. If you have a line array, you do it line by line. And a focal plane array, you take the whole image at once. And the highest resolution and fastest acquisition is only achievable with an FPA detector. So we simultaneously acquire 1024 spectra in just a single scan, which is about 1.5 seconds. And we have an unmatched resolving power compared to other techniques. So this means the highest spatial resolution achievable. So if you only have a small number of particles, then mapping is the approach that is most advisable. So we use an mercury cadmium telluride or short MCT detector that has exactly one pixel. And we detect particles in the visible image. And you see every different particle has its own color. And then we measure these particles automatically, one particle at a time. So this is not a stitched image, but individual particles are measured. And then we have automated methods to create statistics for identity and size of the particle. For a large number of particles, or for highly contaminated filters, we are using the imaging or FPA detector. This has 32 by 32 pixels. And in this case, we measure the whole filter at once, so in one session. This is what you see here is an example what such a chemical image would look like if you measured the whole filter. And this way you also get statistics for identity and size and the visualization of all the particles on the filter. So when we use the mapping approach, we have the Opus particle recognition, finding all the particles based on the visual image as a first step, where we can set a contrast threshold because we're binarizing the image, and define a particle range or particle size range in which we are looking for them. And then we will see all the individual particles that fit these criteria identified, and they are measured automatically. The second step is the particle identification with a program or with a functionality we call MPID, which can also be combined with library search or different Opus methods. And this provides us with a list of particles, their identity, and also an overview over the found particles and statistical information. Okay, when we now go to imaging, we have a step-by-step guidance through the whole measurement of the user. So it's a very easy to use technique. First we collect a visual image. So this looks something like this. This was a very dense customer sample that was not prepared very well. But we still could measure this. So we used the fast imaging of the Lumos 2 and automated data analysis with a software that is called Purency Microplastics Finder, which we will see in action and also its strength in a short time. And so with this combination we could even analyze filters that look like this. So again, the workflow: we take a visual microscopic image, the Lumos 2 collects an FTIR image of the whole filter. Here we see the chemical image of all the particles on the filter. But how does this work exactly, and how long does it take? Here we see a measurement with 100 times its original speed. As the image grows larger, you see the live integration that already gives you a glimpse into the composition. The filter area is about 18 by 18 millimeters in size and is imaged one tile at a time to yield chemical information about the whole sample in order to not miss any particle that might hide in the matrix. One of these tiles contains 1024 pixels, where each pixel is 5 microns in size and comprises an entire FTIR spectrum. At full speed, we are collecting 900 spectra per second. So we are operating at the diffraction limit and are able to get all physically possible information out of the sample while offering unprecedented imaging speeds. And then we use the Microplastics Finder that works fully automated, gives us identity, size statistics, particle list, and all the information you might need along with exportable reports. So what is this Purency Microplastics Finder actually? This is a very easy to use software with a simple interface which basically only requires 4 buttons. You have an import button to load a file into the software, a single file analysis button to just start the analysis of the file you have just loaded, and the results will be prepared and presented automatically, and a batch process. So if you have measured a lot of different filters, you can just run them all at once, maybe overnight when no one is needing the computer. And you have a particle editor that is used to display the results, but also to double check them and look at individual particles. So this is really microplastic analysis at the click of a button. Very simple and easy to use. This is again what the results look like. You have an overview over the number of particles found for each class, a particle list with all the information, identity and size statistics and size distribution. But we will look at this in more detail live on the software. Here we have the Microplastics Finder in action. So on the top you see a list of all the available polymers that are all included with this, and this is again the basis we're using to identify particles, the number of the particles that have been found in each class, and below this, there you find the information on all the different particles, all listed with their size information, where they are found on the filter, the identity, and you also have relevance and similarity. These are quality criteria. So relevance is how sure the algorithm is, or the classifier is, that this particular particle belongs to this class. And when you click on this arrow, you also have this visualized. So here it's absolutely certain this is polypropylene, and below this list there is also the reference spectra available, so you can double check yourself. And second, there is a similarity criteria, which is a correlation coefficient, so the simple spectrum correlation from the measured particle to a reference particle. You can also move around on the filter and then have a look. For example, if we want to get more detail about this particle, we can simply just mark it, and then it will be highlighted in the particle list. Also here you see the information which other classes would have been considered and the comparison to a reference library, so you always know what criteria were chosen to identify this particle, and this is not a black box, but it's really comprehensible what you're doing. This also works the other way around, so if you want to, for example, have a look at a certain PET particle in this sample, you click on this and it will be highlighted on the image as well. There are also distribution parameters, so you can see the size distribution of all the particles found, and you can export this simply by clicking copy to clipboard and enter this into your report. The same can be done for the overall image, and the particle list can be exported into CSV, or you can select the particles you actually want to have in your report, and then you can use this again to provide to your customer or whoever is interested in the information about the sample. Okay, so this is the basic operation, and let's get back to our presentation. So let me sum up all the advantages of imaging we have collected so far. The full process from measurement to evaluation is automated. With the Bruker Lumos 2, you get the ultimate imaging performance for best spectral data, and with the Purency Microplastics Finder, you get an out-of-the-box solution that is based on machine learning and therefore very robust against noisy or bad spectra. And the evaluation is fully automated and done in only 15 minutes. And the presentation of the results is quite comprehensible, and you can always trace what the software has actually done. And this makes it the ideal solution for routine analysis of samples. But I also wanted to show you some samples. So this is a sediment we got from a customer, and here you can see the results in the Microplastics Finder. So we see a lot of PE particles, PVC. You see the distributions on the filter. And, well, again, with this sample we mainly found PA particles, PVC, PE and PP. And another example is sea salt. So this was just dissolved in water, filtered, and then thoroughly washed to get rid of all the salt that may have been stuck to the filter. And again, this is what the result looked like. We actually found a lot of PA and PE particles in the sample. As you can see from the blue color, that belongs to the class of PA, and the purple, no, not purple, pink, that belongs to the PE class. So this was actually heavily contaminated. And here is an example from a milk container that was filtered through a silicon filter in this case. And we see a lot of polyethylene particles, which makes me wonder if this packaging actually was okay. This concludes my presentation, and want to thank you all very much for attending today. And if you have any questions, please feel free to ask them during the Q&A session, or get in contact with us later if you want an instrument demonstration or have any other questions regarding microplastic analysis or the instrument itself. So thank you again, and see you in a minute.